Mars helicopter will fly no more. But there is work to be done and Mars helicopters to do it. We should build dozens and then hundreds as serialized standard spacecraft buses and run a global competition for the best instruments to fly attached to this bus. A fleet of helicopters sent as a continuous campaign every launch window is the best way to get on-the-ground data over any kind of terrain that is vital to the search for life and to the next, crewed, phase of Mars exploration. Why are we going to Mars? Of all the roughly 5,570 known planets in the universe, the one most like Earth is Mars, the next one out from the Sun. A little smaller, a little colder, but otherwise so like Earth that the landscapes are often recognizable because they were shaped by flowing water long ago. Mars' similarity to Earth is motivational for two reasons. First, as an analog to Earth and in particular the period after its formation. Earth's active plate tectonics have effectively erased nearly all its older rocks, while on Mars, much of the surface is many billions of years old with minor alteration. And second, because it is so similar to Earth that humans could plausibly thrive there with current technology. Note that in this chart showing Earth's geological history, the first 3 columns cover just the most recent 10% of Earth's history. If we want to study what Earth may have been like billions of years ago, including the origin of life, we have to go to Mars. How do we get to Mars? The short answer is rockets. In terms of energy, Mars is slightly easier to get to than the Moon, but it takes 6 to 9 months of coasting instead of 3 days, and there's an atmosphere to contend with. The SpaceX Starship is a rocket designed from the ground up to be fully and rapidly reusable, and to be able to transport more than 100 tons of cargo to the Moon or Mars, a quantity that is meaningful in the context of building large bases and cities, rather than dropping off a tiny robot. Mars and Earth's orbits repeat every 2.15 years, so the best time to launch repeats on the same schedule. All planets have launch windows, but Earth-Mars is the least frequent. This sequence gives us a chance to build a programmatic campaign where sustained effort can enable repetition and feedback every 2.15 years. In my view, any launch window to any planet that isn't literally packed with robots is a wasted window. Short summary of exploration and findings to date. United States exploration of Mars began with flybys, orbiters, and landers in the 1970s, followed by a long pause. In 1996, exploration restarted with either a lander or orbiter every other window. Mars Pathfinder, 1996, included a tiny demo rover essentially for Jet Propulsion Laboratory business development. Its success paved the way for the 2 Mars Exploration Rover solar-powered rovers, 2 Mars Science Laboratory-style radioisotope thermoelectric generator-powered rovers, and the Mars helicopter, as well as a few other landers and orbiters. This photo shows Perseverance and Ingenuity, alien robots on an alien planet populated entirely by robots. This campaign of missions has been mostly wildly successful, showing conclusively that Mars once had a climate with running fresh water that could have supported life, along with a bunch of other discoveries. Foreign Mars exploration missions led by Europe, India, Japan, China, and the United Arab Emirates have also made a series of exciting discoveries, including recently the presence of enormous quantities of equatorial ice. Why flight? Ingenuity, the Mars helicopter, was included on the Perseverance rover as a tech demo to prove that Jet Propulsion Laboratory can build and fly on Mars. The general plan is that this new technology will open a door to another decade or 2 of directed missions for Jet Propulsion Laboratory exploiting this advance and further deepening our understanding of Mars. Flying is super useful on Mars. Rover landing sites must be carefully selected to be not too rugged to be traversed, and much of Mars is essentially enormous jumbled piles of incredibly rugged rocks, which are impassable to any wheeled vehicle. Of course, much of Mars is also boring featureless plains, but the rovers are there to explore geology and find interesting stuff. It's not just Mars that is hopelessly rugged. Outside of our roads, much of Earth is essentially impassable to wheeled vehicles. Mars is encrusted with all kinds of cracks and canyons and mountains that make traversal by rovers essentially impossible. I recently used artificial intelligence to upscale the global altimetry map to a resolution of 7 meters, which can help us plan much longer rover traverses in future for instruments too heavy to fly. Flight has been evolved about a dozen times in the animal kingdom, and more than 80% of insects preferentially fly than endure the rugged, treacherous world at their scale. Helicopters on Mars open up much of the planet for direct, high-speed, point-to-point exploration. The rovers average about 3 miles of driving per year, or roughly 100 feet per driving day. Even though a solar-powered helicopter can only fly for a couple of minutes per day, during that time it can move at much higher speed. Ingenuity's speed record is 22 miles per hour, covering thousands of feet in a single flight, and this is by no means the physical limit. Mars helicopter's record and capabilities, in addition to its speed, agility, autonomous flying, and unexpected longevity, the Mars helicopter had several other capabilities. Flying 16 meters off the ground, it could see terrain and features that are otherwise invisible both from orbit and from rover level. A literal bird's-eye view. This was initially pitched as a value add for the rover's navigation challenges, and it proved to be helpful in that regard, but it's also valuable as a standalone capability. It was also amazingly light, just 1.8 kilograms compared to Perseverance's 1,025 kilograms. On the one hand, Mars helicopters will never have large payload capabilities, but on the other, they are so light that our existing entry, descent, and landing technology could plausibly land dozens, if not hundreds, per launch. What is the value proposition? Why do I care? A fleet of Mars helicopters is needed to prospect for minerals. A successful Mars base must have abundant supplies of all its key factors of production, so the productivity of its necessarily limited workforce can be aggressively maximized as quickly as possible. We know that anywhere on Mars it is possible to obtain carbon dioxide, nitrogen, and argon from the atmosphere, as well as the usual silicates, silicon, aluminum, magnesium, oxygen, from rocks. Mars' red color is due to iron-rich dust, but in many places it's a very thin layer. We now know of many places likely to have the copious volumes of mostly pure water ice needed to form the backbone of industry, as well as an essential source of hydrogen. In terms of raw materials, that's a good selection, but any self-respecting, self-sustaining Mars city will need other, rarer elements too, including chromium, manganese, copper, zinc, titanium, lead, nickel, and so on. For the precious metals, a city could plausibly import a stockpile while the supply chain was built, but for the intermediate industrial metals, we will need as much local rich ore as we can find. The problem, we really have no idea about Mars mineralogy. We suspect that Earth geology is much more complex, with a variety of slow aqueous and biological processes gradually sorting elements and concentrating ores. On Mars, we just don't know. There are some very interesting mountains northeast of the Elysium Mons volcanic region, the Phlegramantes, whose origin is unknown, which is low altitude enough for Starship to land, which has water ice, and is close enough to the equator to support solar power, but it would be very silly to invest billions in a Mars city only to find out that the mineral-rich province of Mars is 4,000 miles away. Somewhere on Mars there will be the equivalent of the Bushveld igneous complex, and we should find it as soon as possible. A close-range aerial survey using a mix of sensors is the best way to cover a lot of ground and build up our knowledge of various areas. The next Mars helicopters will build on Ingenuity's success to provide a flexible platform for Mars surface exploration. A fleet of 50 to 100 independently operable robots set up to run surveys over large swaths of land, for example, following an entire river system or candidate human landing site. Some will carry remote sensing equipment, cameras, radars, spectrometers, magnetometers. Some will carry surface sampling equipment and specialize in landing next to cool-looking rocks to drill them, laser them, or X-ray fluorescence them. Each helicopter will support just one instrument, but the entire fleet will support dozens of different kinds, increasing opportunities for interested scientists to build and qualify relatively cheap instruments on a standard bus, then iterate for each launch window opportunity. Jet Propulsion Laboratory faces an existential challenge in a world where Starship exists. Jet Propulsion Laboratory's major specialty is slowly building expensive one-offs that are reliable and, above all, light. If Starship obliterates the mass constraint, then the barrier to building Mars rovers gets much lower for anyone else, eroding Jet Propulsion Laboratory's competitive advantage. A fleet of Mars helicopters initially delivered using the Mars Science Laboratory entry, descent, and landing system is a great on-ramp for transitioning to much bigger science and serial production of numerous copies of the same design. It also allows progress towards the goals of Mars sample return while other architecture issues are ironed out. Design and concept of operations. The obvious Mars helicopter scale-up is the Pathfinder, Mars Exploration Rover analog. A much larger helicopter built on the same plan and festooned with sensors. Unfortunately, this will not work, because it is too heavy. Mars's gravity is about 38% of Earth's, making flight easier, but that's it. Everything else makes it harder. In particular, the atmospheric density is barely 1% of Earth's, and the temperatures and thus speed of sound are lower too. Meanwhile, the Sun on Mars is about 2.5 times dimmer than on Earth due to greater distance. All things considered, flying on Mars is about 5 times harder than on Earth, and even on Earth turbine-powered helicopters are an engineering abomination kept aloft mostly by Earth's malicious contempt at the prospect of allowing them to touch the ground. What this means is that while Mars helicopters don't have to be super small, they do have to be thin, or flat. Very little mass per unit area of propeller blade. There are a few tricks that can help, which I'll explain with the help of this sketch I made in 2017. First, it's a hexacopter and each propeller has 6 blades. This increases the disk area and amount of foil available. Other configurations are possible, but 6 blades is a good compromise on a bunch of axes, explored in more detail by actual Mars helicopter engineers in this paper. The hex planform is flat, which assists with packing in the aeroshell. It has plenty of room in the middle for a solar panel. It has an easy way to build wide-spanning legs to prevent tipping. It's robust to the loss of 1 and possibly 2 rotors. The broad solar panel and extended legs can readily contain the phased array antenna elements necessary for the helicopter to communicate with orbiters or even back to Earth directly. The Mars hexacopter is packed in with a bunch of others in the Mars Science Laboratory entry, descent, and landing aeroshell, exactly as featured in the first 3 minutes and 15 seconds of the classic 7 minutes of Terra film. Then, instead of the giant rover and its sky crane, the helicopters can be dropped one by one from the parachute-supported back shell like skydivers out of a plane. Using terrain relative optical navigation, each can self-land under battery power, phone home, then begin exploring. The backshell itself is usually expended by crashing into the surface, but if desired it could be fitted with its own shock-tolerant electronics as, for example, a fixed weather station and local radio repeater. Ingenuity was a tiny tech demo, a flying version of the Sojourner rover. It featured coaxial counterrotating blades and, like Sojourner, had essentially no scientific payload beyond engineering cameras for navigation. The next generation of Mars helicopters must be significantly more capable. Payload sizing. The Mars helicopter's blades were 1.2 meters long from tip to tip. A Mars hexacopter using blades at this scale would be roughly 4 meters wide, with a mass budget of 15 to 45 kilograms, depending on whether we're maximizing payload or range. There's a balance to be struck between mass for batteries for speed and range and mass for instruments, but with 5 kilograms of batteries a flight time of 20 to 25 minutes and daily range of 20 miles seems quite achievable. Over the course of a 2-year mission, one helicopter could cover 14,000 miles over arbitrarily rough terrain, enough to fly all the way around the planet. Perhaps one mission can stage this feat as an endurance race between competing designs. The basic planform could be scaled up and down in size depending on preference, but provided the mass per propeller disk area can be kept low, larger is better. That is, larger drones have larger, slower-moving propellers with better drag characteristics and longer flight times. Larger payloads can carry more capable instruments and have better thermal mass. The natural limit might occur at around 10 meters diameter, deployable from Starship, where the lack of section would require unacceptably high structural mass to prevent the hexacopter from flopping around like a wet noodle. A vision for the next phase of robotic exploration of Mars as related by Eric Berger, the Mars helicopter's forced adoption of modern computers and commercially available off-the-shelf electronics has opened a new era of exploration and opportunity on Mars. Our learnings from orbiters, landers, and rovers are mature if not tapped out, relative to what we will learn from fleet after fleet of relatively inexpensive, mass-produced helicopters.